I'm going to walk through an example of unsupervised fine-tuning of Llama 3 on a low-resource language, namely Irish. First, I'm going to prepare a dataset using a Wikipedia dump of Irish language articles. I'm going to push that to HuggingFace, then I'll blend in a small amount of chat data to make sure there's no catastrophic forgetting. And I'll then do one epoch of training on that dataset before doing a short period of annealing at the very end. I'll walk through each of these steps one by one. I will say that I could do longer training and there are some further tweaks I could make to get better performance, and I'll talk about those right at the end. As a little taster, here's a look at the dataset I've prepared, and I'll show you how I prepare it. It's Trelis, GA for Gaeilge, that's the Irish word for Irish, wiki. And I have this dataset of 57,000 rows, and you can see here, each of the rows is an article from Wikipedia. It's actually the title of the article, followed by the contents. And I've also calculated the number of tokens here, just to make things easier when it comes to deciding the length we want to train on. So this is a rather, I wouldn't say it's large compared to the amount of tokens used for pre-training. It's actually quite small, but it's quite a large fine-tuning dataset. And what I'm going to go through is fine-tuning on that dataset, blended with some chat data, to do one epoch of training. And that's going to allow us to take a look at some of the loss curves. You'll see that I'm able to get my training loss to come down fairly smoothly. And over time, I'm also able to get the eval loss in the key run here. It's this light blue one. I'm able to get the eval loss to decrease, which means that we're fitting that Irish data a bit better. Although I could have run for a bit longer. So let me take a step back and just outline the high-level steps we're going to take. I'm going to walk you through preparing that data set I just showed you, which involves extracting the data from a Wikipedia dump. Then I'm going to process that data very simply and push it to Hub. I'll then load the Irish data set in a Jupyter notebook using HuggingFace, and I'm going to blend in some chat data. That's to avoid catastrophic forgetting of the model, and also make sure it maintains its chat format. Then I'll walk through the fine-tuning. I'll walk through the setup of using LoRA with rank of 128 and making the embeds and LM head trainable. That's important so that we get close to the performance of a full fine-tuning, or perhaps even better, because we've got regularization benefits of LoRA. We're going to train for one epoch, although really it would be better probably if I train for longer. And then I'm going to do some annealing for 0.1 epoch. So I'm going to train with a constant learning rate. And then at the very end, I'm going to allow the learning rate to slowly decrease. And that's a technique that can help improve the final perplexity of the model. And lastly, I'll just make a few quick comments on things I think I could have improved on, or little additions you can make to get an even better outcome. So with that, let's take a look at the dataset preparation. I've got a notebook here called Trelis WikiExtractor. It's based on the GitHub repo called WikiExtractor. So you can check that out online directly if you would like. I have it referenced just up here. So what I've done is I've set up HF transfer that allows for fast download and upload of data from HuggingFace. I've installed WikiExtractor, and then I've set up the URL from which I want to grab the data. Now let's just take a very quick look at what the Wikimedia website looks like. So here we are, Wikimedia downloads. I'll go to database backup dumps, and this is separated according to different languages. So here's a wide variety of dumps of data, and the one that we're interested in is GA Wiki. So it would be EN Wiki if you wanted the English. So yeah, you can see there's a partial dump of books. You can also get books, which would be useful, to be honest, in improving performance. So yeah, lots of English data there. But what we want is GA Wiki. So I'm going to go to this GA Wiki partial dump, and I'm going to see that it was last dumped, which I think means the full dump on the 1st of May. So I've gone to that page and I've got the complete dump. And what we're interested in here is the full list of articles. So we want the pages and articles, so we can download this here. It's 34 megabytes in compressed form. So uncompressed, it would be larger. Now, something to note is this is quite a small amount of data. There really isn't that much Irish data available on Wikipedia. it's orders of magnitude less than what's available on the English language Wikipedia. And that is going to be an issue because it makes it kind of insufficient if we want to get really high performance in Irish. So although I'm going to show you how to fine tune on this Wikipedia dataset in a later video, we'll need to include much more data from the Common Crawl or maybe from books in order to improve the quality of the fine tuning. So this anyway is going to be the file that we want to target. So let's go back to Wikipedia, and we've got this file specified here. And we're just going to do a wget request in order to download that data. So I'll run that now. And that should all download into a folder, GA-Wiki. And I just want to show you the data. Here's the date. And if I click into that, let me just see. Yeah, I haven't yet extracted. So let me actually run the extractor here. And while I'm waiting for the extractor to install, I'm going to inspect a tiny portion of the file that I have downloaded. So this is just printing first 20 lines. And you can see what this raw data looks like. You've got Media Wiki, and then you have these namespaces. And you can see some headings here: Man, Specialte, Discussion, Plays, Discussion, Usajor, that's user. So you can see here all the typical kind of headings you would see on a Wikipedia website. So this format now we want to get into a cleaner format that we can then make a data set with. And the way we'll do that is using WikiExtractor. So WikiExtractor takes this information in this format and it produces a JSON line type format. So it's going to return a clean JSON type format. Now that we have WikiExtractor installed, what we can do is start to run WikiExtractor and extract the data from this format into a clean JSON format. Now to do that, I'm going to check how many cores I have. So, wow, I have a lot of cores. I'm actually running here on a H100, which has a fairly large CPU, so that's pretty nice. So we're going to use all of those cores, and it's going to extract the data into that JSON format. And I did this earlier with 2 cores on a collab notebook, and it took me probably about 10 minutes, maybe longer, maybe like 20 minutes. So let's see how long it takes here. And then we'll just print. We'll print where it's extracted, and I'll just show you the format that it's being extracted to. So actually we can already see it's being extracted to this AA folder, and you can see each of the wikis. You can click in here and it will show you the data. So you can see everything has got its own line, although there's wrapping here in this viewer, but every line has got an ID, a revision ID, a URL, a title, and then the text. Now notice how some of these entries have no text. And if they have no text, we're not interested in them. So we're going to filter those out. But if they do have text, like this one here, title is Mathematic, which is mathematics. The text here is something that we're going to want to keep. So we're going to want to keep this row. Okay, so now we have all of the data has been extracted. It was pretty quick because I've got a lot of computer cores. By the way, a CPU is what you use for doing that. It's not parallelizable using a GPU. So we've extracted everything. And there's just the AA folder. So for English, there would be many more folders because there are many more articles. So it would separate it into more folders here. All right, so moving on, we have the creation of a HuggingFace dataset as our next goal. So we'll install HuggingFace Hub. Now I won't run all these cells. And what we're going to do then is start to process the files. Now processing is best explained just by showing you the actual dataset. What I'm going to do is I'm going to take every row in the JSON file that has text. So I'm going to throw out all the rows first that don't have any text. And the ones that do, I'm going to assemble a column called text that is a combination of the actual text in the article. But I also want to include the article title, a full stop, and then a space. So you could probably just include the article text, but I like including the title. It just adds a little bit of context. So here you have CLG, Common Lucas Gael on Schleve. So this is a sports club actually, and then the description. But you see I've just added the title in here. So that code is what I'm doing here. So I'm basically going through all of the files If there's text present, then I'm grabbing the title, I'm grabbing the full text, and I'm basically putting the title with a full stop and then the text. So that's how I'm assembling the data set. And when I run that, I'm then able to inspect. So I can inspect here, and actually here's CLG on Sleva. It's the 4th row. And you can see how it's the title followed by that text. And once that's done, I can push my data set up to Hub. So I save it to disk first, but then I can push it to Hub and get my data set ready to be used later on. Now, there are two just other things I want to show before that. One is I've created a plot here of the token distributions. So basically, I have counted how many tokens are inside each row. And I'm doing that using the Meta Llama 3 8B instruct tokenizer, so the Llama 3 tokenizer. And then I plot a histogram. So you can see here that most of the rows are below 5,000 tokens. But we have a few that are actually going up to 25,000 tokens. And there are actually a few beyond that going up to 100,000. It's just the graph gets very cramped. Anyway, this is useful to know because it tells you what kind of data lengths you have. We're going to train on a length of 8,000 tokens. So basically any of these rows that are longer than 8,000, they're just going to get truncated. Now, ideally, I would design a way to wrap that into new row. So I would make all of my rows less than 8,000 and just take anything that's truncated and put it in a new row. So that would already be an improvement you could make on my data set. My data set here, by contrast, it just has rows of all the data. So some of the rows will be really long and some of them will be really short, and we'll just truncate them for now. And that is pretty much the last improvement. You can see I've listed the token count here so that you know when it comes to preparing your data set, you can more easily filter without having to retokenize that data. So now that I've got the data set ready and I've pushed it up to Hub, we're going to start to work on the fine-tuning notebook. And in that notebook, I'm going to blend in a little bit of data. So I'll talk about that now. I'm going to fine-tune using unsloth. This is going to give me a 2x speed up in LoRA fine-tuning versus just using transformers. However, unsloth doesn't support multiple GPUs, so that is a trade-off. If you wanted to train something larger than Llama 70B, it's probably going to be more efficient to use a multi-GPU setup. And you can look at my multi-GPU video if you're interested in how that works. So first off, I'm going to run the installation. There are a few installations of packages like Datasets, HF Transfer for quick transfer, HuggingFace Hub, and also weights and biases so that we track the data during the run. So I've run those, they're all installed. And then we're going to install unsloth. Just notice I have two different ways you can try. If you run into issues with the A6000 type install here, you can try this installation method here. Now, there's something pretty important, which is once you do the install with unsloth, I recommend just shutting down the kernel. So go to kernel and shut down or restart. And that will make sure that you're using the latest versions of the installed packages. I should note, by the way, that if you're using RunPod and there are instructions up here, you can use a one-click template that I've prepared. That will already set you up with CUDA 12.1, and it just gives you a clean slate that's going to be more reliable for doing the installations because unsloth can be a little bit tricky. So with unsloth installed, we're going to load the model. Here I've specified Meta Llama, so it's Llama 3. And next up, we're going to load the model and the tokenizer using unsloth's fast language model. You'll notice I've set the max sequence length to 8,192. And unsloth will automatically detect that my GPU supports brain float 16. And I'm not going to quantize, so I've set load in 4-bit to be false. With the model loaded, I like to check that there are no weights on Meta, which means there are none on CPU. They're all correctly loaded to GPU. And then I like to print, just as a check, the maximum position embeddings, which is 8192, and that matches my max sequence length, and also the EOS token. So the end of sequence token here is going to be EOT, And we're just going to check, actually unslot sets that for us automatically. If you're using transformers, which is also supported by this script, it will be set a little bit down below. So here we would print the tokenizer, and moving on, you can see there are a lot of special tokens in Llama 3. Moving on then, there are a few other checks to make. So first we want to print BOS, the beginning of sequence and end of sequence token. You can see how Unsloth has already set the end of sequence token correctly for us. Otherwise, you can do it manually. The pad token is set by Unsloth to one of the reserve tokens. This avoids having to increase the size of the tokenizer, as in the number of tokens in it. That's good because it means you don't need to retrain new tokens. So here, just in case you're not using Unsloth, you can manually set that pad token to this reserve special token. Lastly, I just have a few checks that the model pad token is matching the tokenizer pad token. And then I print out all of the special tokens. Typically, if you do add a new token for padding, you need to resize your embeddings. This is what's happening here. Actually, it won't be resized because it's already a multiple of 16 and all tokens are accounted for. So if you run that cell and you've added to embeddings, and you've added to tokens, it will increase the size of your embeddings. But if you used Unsloth, it's not going to change anything. Lastly, you can check out a test chat template. I've just made this little conversation, and you can see here, this is the format of what the chat looks like when it's been templated by the Llama 3 template. Last of all, I do a quick check here where I tokenize a simple test prompt, and I add in special tokens, which by the way is default to true when you tokenize anytime. And this just shows that when you do tokenize a prompt without any chat templating, it will still add in a beginning of text. And this is important to know because we are going to be tokenizing text without a chat template. And we want to know what the behavior is when we just tokenize a string of text. And this shows you that the behavior is to start with begin of text. And that's a good thing because it indicates to the model that every new piece of text from Wikipedia will start with begin of text. And the other thing we want to know is how will that end? And actually, when we get to the SFT trainer, when we decide to pack the examples, automatically they'll be packed with an EOS, an end of sequence token between each of the phrases. So actually, when you tokenize something like test prompt, when we pass it in, it's going to look a bit like this. So let's just say we've test prompt, and then it's going to have an EOS token at the end, which is, I think, EOT ID. And let's see if I've got that right. Yeah. And then there would be your next test prompt. So after that, you're going to have test prompt 2, and that sequence will continue on. So yeah, I'm just highlighting this nuance because it is important how you pack the examples, and we want to make sure that they are being packed with this EOT because that trains the model to finish when it's finished with responding with a piece of text. And it's also nice to have this beginning of text because it just gets the model used to knowing, okay, this is the beginning of a new conversation here, even if it's not chat templated. So next, a few more checks that the model and token vocabularies match, which they do, before which we can move on to fine-tuning. So in fine-tuning, we're going to use LoRA. That's going to be better probably than full fine-tuning because unless you're doing pre-training, it tends to be more stable to just fine-tune adapters, which have a lower rank than the base model. If you try to fine-tune every parameter, it can risk overfitting. However, we are going to fine-tune with quite a lot of data, so we need to use a large rank for the LoRA fine-tuning. And we're going to target certain modules. So we'll target the self-attention. So we're going to target Q, K, V, and O projections. And we're also going to target the linear layers here in the MLP, so gate up and down. I think for Irish, given that the meanings of the words and the kinds of the subwords we're going to see are going to be different to English, there probably is some value in at least training the embeddings just to make sure they're adapting to Irish. And to some degree, then it makes sense to train the LM head. So I'm not entirely sure the importance of those because I haven't run an ablation, but my guess is that you do want to train the linear layers, plus you want to make the embed tokens and the LM head trainable as well. So with that, we're going to explicitly do what I just said. I've listed here all of the linear layers I want to make trainable, and I've listed here the modules to save. This will make embed and LM head trainable, but not apply LoRAs. It will actually make them fully trainable. And even more, Unsloth will upcast them for float 32. So it's common to have, in particular, the embeddings be in float 32. It just adds extra precision for the representations that we give to the input tokens. Because we have made those trainable, the embed and LM head, we have actually a large percentage of trainable parameters. This is also because we've set the LoRA value, the LoRA rank to 128. Often for smaller data sets, we just set that maybe to 8 or to 32. But for a larger data set, I think having something larger and more granular makes sense. Notice how I'm using RS LoRA, rescaled LoRA. This will adapt the learning rate of the adapters. It will actually increase the learning rate of the adapters relative to the learning rate of, say, the embedding layers or any other layers we're training normally. And this is because if you're training a smaller number of parameters, you can basically move in that optimization space faster. You've got here the LoRA alpha value of 32. This is typically what I would recommend setting it to for actually a wide range of models, anything from 1B to 7B or even 13B. As you get up to 70B, that's going to be a larger model. You probably want to increase the LoRA alpha a little bit more. You can take a look at my explanation of that in the REFT video, if you like, or I think I have a video covering rescaled LoRA on its own. So with LoRA set and with the trainable parameters calculated, really just for informational purposes, we can move on and set up evaluation. So this is very similar to videos I've shown before. Basically, I create a custom data set of questions and answers. And this just allows me to manually inspect how the fine-tuning is going and if performance is improving from that perspective, because in parallel, I'm going to have a validation data set that would tell me how I'm doing in a more numeric sense. Now, to get this data set here, what I did actually was head over to my raw data set, and I just picked out a few rows, like maybe this row here, and I copied the data, and I asked ChatGPT to generate a question and an answer based on this information, grounded in this information. So that's how I kind of sped up the process here. And we have a few questions around ozone, around the Blarney Stone, if you've heard of that, a publisher of a book called Monine, and a question on founding a college, and then reasons for why there was the city called Jos, which I believe is in Nigeria, why that city was founded. So then I run the evaluation and get the answers here. And just a few interesting things. So you can see, even though the question is asked in Irish, the model responds here in English. That's also the case here. When we ask about the Blarney Stone, it responds in English. Now, interestingly, in some questions, when we ask in Irish, it will respond in Irish. So it's kind of inconsistent, and that's certainly a behavior that we would want to improve with fine-tuning. Now, I'll note that if you wanted to correct that, well, you've two approaches. One is you can simply add a system message. I did this earlier. If you add a system message that says respond in Irish, the model will just respond in Irish. Llama 3 is strong enough to do that, even in the 8 billion parameter form. So that's a very simple fix. But even if you created some chat data sets, even maybe 12 examples or something like that, you should be able to get the model to adapt to responding in Irish if the model is asked a question in Irish. So I don't really think that's of particular difficulty. And so I'm not too concerned about that behavior. What I really want to do is improve the ability of the model to, to improve its knowledge of the Irish language, because when you do look at an answer here, you can see, and it's kind of hard for me to describe this, but if you read through the Irish, you'll find some examples of where the grammar isn't exactly correct compared to, what it should be. And just as a further example here, you can see within this answer that there is a degree of repetition happening in the answer that was provided in Irish. So these are the things that we're going to try and improve upon. Next up is dataset loading. And here I'm not just going to fine tune on the Irish data, and there are two reasons for this. First off, if you just introduce a new language dataset, there's a risk that the model is going to catastrophically forget some of what it knows on coding, some of what it knows on English, some of what it knows on general knowledge. So to avoid that, what you can do is blend in a very small amount of data, like 5%, ideally containing a representation of what the model was originally fine-tuned on. Now, maybe there are some better choices, but I'm going to use this dataset here that Maxime Lebon has put together. And it's a dataset that actually allows for ORPO support. We're not going to do ORPO or DPO, but we are going to make use of the chosen column within that dataset. So here we have this chat format. Everything is in this list of messages format. And what we're going to do is take the data from the chosen column here. And we're going to blend that in a ratio of 20:1 roughly. So you can see here the blend size will be 5% of the base dataset, the base dataset being GA Wiki. And further, what we're going to do with Maxime Lebon's dataset here is apply a chat template. So we're actually going to format it in the way that Llama expects. And what this means is that 19 out of 20 samples are just going to be this string of text with the beginning of sequence token and an end of sequence token. We're not going to chat template that because it doesn't really make sense to put a Wikipedia article into a chat template. But 1 out of 20 of the entries in the dataset are going to be the actual chat template with data from Maxime Lebon's dataset. And you can just check out the kinds of data in this. So it includes things like maths preferences. It includes ORCA DPO pairs. So it's got a fairly wide set, hopefully, of data types. It also has data for decensoring the model. That's not something that you might necessarily want. So I'm actually going to exclude that when I'm loading this data set here. You can see right here, if the source is the toxic DPO, which is the decensoring, I've just pulled that out. So I'm left with the other data sets around coding, maths, English, chats. And so by the end, we're going to be left with this blended data set that should avoid catastrophic forgetting. And it should also maintain the chat templating. So we don't need to do further chat templating after this fine tuning, or at least we minimize the need for doing later steps of SFT or ORPO. Now, once I have that data set, I'm splitting it in a 95:5 ratio so that I have a test split, or validation split is really what I'd prefer to call it. But HuggingFace has this nomenclature of train test. So anyway, I'm left here with a data set now, 95% of my blended data and 5% of my blended data set aside for test purposes. You can see here about 57,000 rows in the train and about 3,000 in the test set. And here is an example of the data. This example here just contains text. You can't see the beginning of sequence or the end of sequence token because those are going to be added when the tokenization is done within the SFT trainer. Moving on now to the trainer setup. We're going to train for 1 epoch and we're going to use a constant learning rate. I want to talk a little bit about that, but first let's talk about the virtual batch size. Running on a H100, I have a batch size of 2. I think actually I could fit a batch size of 3. And then I make the product of batch size and gradient accumulation be 32. So my virtual batch size is 32 and gradient accumulation is 16. My fine-tuning tag is Gaelga. This is just creating the name for the new model, which is going to be the base model name followed by the fine-tuning tag. Now notice that we're going to do unsupervised fine-tuning. So fine-tuning on all of the data. That means we're not training only on the completions. So I've set that flag to be false. Moving on to the SFT trainer, just a few notes. I'll always run for just one step. First, check that everything is running. I'm not running out of memory on CUDA. The number of save steps are 0.5, so I'll save the model halfway through the run. Packing is true. This is important. This means that my samples are, if they're smaller samples, they're going to be packed together to fit within that 8,000 context length. And that's good because if you're training with pad tokens, you're just kind of wasting forward and backward propagations. So you really benefit just by packing your data in. An SFT trainer does this automatically, and it does so by adding a concatenation token, which is adding an end of sequence token between those packed examples. And if you check the documentation, you'll find that just by setting packing true, it will automatically put a concatenation token right between your data. Now, the column that I'm using from the dataset is called text. So you'll see that in my dataset as I've built it. There are two columns. There's text and there's token count. And the one that we're going to use is text. Moving back to my trainer here. So my max sequence length, this here needs to be set to the same value as I had earlier. So actually I'm realizing that this is a mistake I didn't see earlier. So let's see if we can find max sequence length is set here. And this actually needs to be set to max sequence length. So this was actually a mistake. I had it too low, so that would impact the performance of the training. Shouldn't give bad training, but it just means I'm not benefiting from training on the full context length. It may also, by the way, affect my batch size. It means that you can't fit as many batches if you've got a longer sequence length because it takes more memory. Logging steps. So every 10 steps, I'll log the training loss. Training for one epoch. This is my output directory. I'm evaluating every X number of steps, actually every 0.2 of the total steps in the entire run. So I'll be evaluating 5 times during the run. Here's my batch sizes, then my gradient accumulation, which is already set above. I talked about that. I'm setting BF16 to true because I'm on an Ampere GPU or later generation. And my scheduler type is constant, so constant learning rate, which I'll talk about. Setting the HuggingFace Hub repo to private, that's up to you to decide. The warm-up ratio, this allows you to increase the warm-up ratio slowly towards the start. It can also help avoid catastrophic forgetting. Basically, instead of the model being jolted by the first data points, it's kind of more slowly brought up to the full training rate. Now, the learning rate I'm using here is 5e-5. This is perhaps on the higher side, like you could maybe use something like 2e-5 or 3e-5, but you'll see in the loss curves that the training looks reasonably stable. So I think in hindsight, this was probably a good choice for that learning rate. Now, I'm going to use gradient checkpointing. This means that all of the activations are not going to be stored on the forward passes to save memory, and they'll be recomputed during the backward pass. Last off, I'm going to report to weights and biases so that we can save all of the data from these runs. And actually, as opposed to some of my other scripts, I've made some improvements here on weights and biases logging. You can see here that I'm initiating a project and a run name. So this run here is all data rows. And just by applying this tag, it allows us to nicely compare some different runs that I'll talk about a little bit here. And with that, I'll run the training and run it through all of the steps, which is something I've done earlier, and I'll go through those steps, and then run an evaluation afterwards. And after I've run the training, this is just with constant training for one epoch, you'll see that in the evaluation here, I'm still getting answers in English, although I'm now getting more answers in Irish. So the model is providing more answers here in Irish. I wouldn't say the answers are all correct. For example, here it thinks the location is in Kerry when it's in Galway, in fact. However, that being said, you can't expect the model to memorize knowledge just by passing through one epoch of data, unless you have an extremely large data set that's covering that knowledge from multiple angles. And remember that the Irish Wikipedia is quite limited in scope. So we don't have the same benefit of English, where Wikipedia is going to cover a lot of topics from a few different angles. Now, when we do incorporate some common crawl data, maybe that will help give us some extra angles and help with some memorization. But just running one epoch on the amount of rows that we have, I don't think we could reasonably expect the model to pick up that data from a memorization standpoint. So let's move over and take a look at the results that we get here. And then I'll talk a little bit about learning rate and why I ran annealing afterwards. So here I have the results in weights and biases from 3 different runs. I have a run on an A6000, then a H100, and then another one on a H100. And what I like to do is start by running just on a small number of rows. So I've run on just 1000 data rows on an A6000. Then I repeat it on a H100 just to see how much quicker it would be. And just to give you a sense of speed, I can show you here the runtime on these runs. And the way I'm measuring this is in the number of samples per second, training samples per second. And you can see very roughly that running on a H100 is roughly twice as fast as an A600. Now, the number of samples are even higher when I run on the full data set. And I think that's because when I run a larger amount of data and I still have the number of evaluations, the evaluation time is having less of an overall impact on the average time. I'm not entirely sure on that, but for sure, I'm seeing a significant speed up, as you would expect, in running on a H100 versus an A6000. So let's take a quick look at the training losses, and you should be able to see the training loss clearly here. Actually only for running the full amount of data, because I only had logging every 10 steps and it only took 13 steps when I had 1000 rows of data. So you can only see one data point for the training loss there. But you can see that the training loss looks good. It's falling, it's fairly stable, and it's not oscillating wildly. So my choice of virtual batch step is probably good. My choice of learning rate is probably good. My choice of epochs is probably too short because you can see my training loss is still falling by the end of the training. Now, if we move up and take a look at the eval loss, you can see here how it is also falling. And this is a good sign too. It's falling monotonically, which means again, my learning rate is probably good, as is my batch size. It is still falling though. So my number of epochs probably should be a bit longer, or possibly you could argue my learning rate could be increased by a little bit as well. Now, I want to talk a bit about learning rates, and I'll show you just hopefully with a simple whiteboard demonstration. I just want to illustrate a few different learning rate options. And for that, let's just draw a graph here of the learning rate versus time. So we've time here, and on the y-axis, we have the learning rate. And we'll start off with a simple cosine example, or rather a constant. So if you have a constant learning rate, it's just going to be something like this. So we can mark that as constant. And the other common learning rate is cosine. So let's pick a color here for cosine. And in a cosine learning rate, it's going to fall something like this. So we put in cos here. And the nice thing about cosine is that as you start to train the model gets better and better and better. And the updates you need to make are smaller and smaller. So it makes sense that you reduce the learning rate in order to kind of get into the nooks and crannies of the optimization surface. However, the drawback of cosine is that your learning rate is slowing. And so if you're slowing the learning rate too soon, you're not going to be able to train as quickly as you might otherwise do. So there's an approach that kind of blends the two of these that is quite nice. And that's constant plus annealing. And the idea with constant plus annealing is when you get to the end of your constant process, you do an extra step. Maybe you stop your constant a bit early. It doesn't really matter where you stop it. But what you can do is add a short annealing step that will just take the learning rate down. So here you go constant, and that keeps up your speed. And then you add annealing at the end, which kind of slowly brings the model back down in a smooth way to optimize into those nooks and crannies. So this is the idea of doing annealing. And I'll just put down ANN here. And this is really what we would like to do, a constant learning rate and then annealing. And just for the sake of completeness, you'll notice earlier in my code, I showed using warm-up steps. What warm-up does is instead of starting off at this point, it would actually slowly warm up the learning rate. So you would start here, slowly increase, and then you would either do cosine or you would do constant, and then have an annealing step at the end. So I've actually implemented the annealing step, and it's pretty much the same as the original run that I did. I did it 2 days apart, so my data sets are randomized a bit differently, which means that the losses won't be continuous, but I'll show you anyway. And the only change I've made here is during the training, I've just set the number of epochs to 0.1. And so I've loaded a model that was already trained for 1 epoch. You can see right up here when I specify the model name, I'm loading a model that's been fine-tuned for 1 epoch. And then I do 0.1 more epochs of fine-tuning. And the 0.1 epochs I do are going to be done with cosine. Now, you could also choose linear. It's fine if you just go down as a linear curve. What I showed here is a linear reduction, but for annealing, it's going to be basically the same. Arguably, maybe a little bit better if you just do a cosine annealing towards the end right here. So I've run that, and I can show you now the annealing. And you'll see here, first on the training loss, the annealing, of course, is much shorter. It's 1/10 of the length. You'll see that my training loss is falling. It's actually falling at a significant rate here on the training curve. And there's that discontinuity because my data set is shuffled differently. So you can see here, my data set is a bit different in training loss to how I finished yesterday. And if we go up to the eval loss, you can see here that I'm just annealing the data set towards the end. And you can see the loss is falling there. Again, it's not exactly continuous with where things left off yesterday because of dataset shuffling. And now with that annealing done, I can take a quick look at the answers. Here we have the answers right after the training. So this time with the question in Irish, we're getting an answer in Irish, and we're getting an answer in English for the second one. We're getting an answer in Irish for the third one, an answer in Irish for the fourth one, and an answer in Irish for the fifth one. Now, there are still issues here. For example, there's still this issue of repetition in the answer here on Nigeria, although the city is now correct. Joss, it's getting the right country of where that city is. So that's good. So overall, I would say that probably the model is improving just based on the eval loss. Certainly the perplexity is going down versus the Wikipedia dataset, which is of high quality. As I mentioned earlier, this is quite a limited data set, so we're not hitting the model with the right number of angles or the quantity of data that would ideally be used for fine-tuning or certainly for pre-training. But that's something maybe we can address when we use a larger data set and incorporate information from books or the Common Crawl. Now, I have pushed the model up to Hub, and I'm just about to push the example of the model that has been fine-tuned. And it's available at Trelis, and I can just look for Gaeilge here. And we have the Llama 3 instruct model available. As I said, I'll push up the one now that has got the annealing step as well. And that is a quick overview of unsupervised fine-tuning on a custom dataset extracted from Wikipedia. A few updates and improvements that could be made. As you saw, I made a mistake on the length that I put into the trainer. I should have been using the full 8,000 tokens worth of length. So that should improve performance a little bit. Second of all, the dataset I had is limited in scope. Expanding that dataset could lead to improvements, and that's something we'll look at in later videos. Now you notice that my training loss was still falling. So we had the opportunity to reduce the eval loss by even further if I'd increased maybe to 2 epochs or 3 epochs on this dataset. Last of all, it's probably helpful to add some supervised fine-tuning or ORPO on top of this pre-training, this fine-tuning pre-training that I've done. That would require us to generate a chat dataset for the Irish language, something that we can also think about in later videos. That's it for this video. Both of the scripts are available in the advanced fine-tuning repo in the Wikipedia branch, and you can find links to the models and to the dataset below in the description. Let me know your comments below, as usual. Cheers.